This is AP Calculus BC, and in this video I'm going to talk about section 9.5, and the title of this section is Comparison Ratio and Root Tests. There's actually 4 tests that we're going to talk about here. There's what we call the direct comparison test. There's another one called the limit comparison tests. Then we have the ratio test and the root test. So there's 4 tests altogether that we're going to look at. Now, up to this point, we have talked about geometric series. We've talked about telescoping series. We've talked about the nth term test, the integral test, and the p-series test. So we've got a few more of our tests listed out here. This would take us up to 9. We're going to learn 10 altogether. And they all can be applied in different situations. So there's really, when we start talking about these convergence tests, it's really a matter of looking at the series that you have and using the test that's the most appropriate based on the type of behavior that you see in that series. So the first test that we're going to look at here is the direct comparison test. And you may or may not remember this one from section 7.8 when we were doing improper integrals. There was a problem towards the end of the notes that I told you to make sure you take a look at. And the idea was we could figure out the convergence of an improper integral based on looking at a function that was similar to the one that we were looking at, but maybe slightly larger. If the larger integral or the integral of the larger function converged, then that means the integral of the smaller function would also converge. So we're using that same general logic when we go through these types of questions with the direct comparison test. So for this first one here, we're trying to see whether or not this series will converge. And we're looking at natural log of n over n, and that's going from 1 to infinity. So from the first term to the infinite term. And we can do this one by a direct comparison. So what we're looking at here is the fact that once we get past n is equal to 3, then natural log of n becomes greater than 1. So once we're past the third term. And with that being the case, that means after we pass the third term, natural log of n over n is always going to be bigger than 1 over n. So if we think through that, the larger of the two functions is the natural log of n over n. Well, 1 over n is a series that we know, right? That's the harmonic series. We know that one diverges because it's harmonic. We also know by the p-series test or by the integral test, any of those would show that this diverges. So since that one diverges and we know natural log of n over n is a little bit bigger, that means this one also must diverge. Okay, so that is what we call the direct comparison test. Now, the direct comparison test can also be used to show convergence, but the big thing is you have to be concerned with the magnitude of the two functions that you're comparing. Okay, so here's essentially how this test works. So if the bigger of the two series that we're comparing converges, that means the smaller series will also converge. If the smaller of the two series diverges, that means that the larger series also has to diverge. So B is what we just looked at. So we looked at that scenario. We had, natural log of n over n being a little bit larger than 1 over n, and the smaller of the two was diverging, so the bigger one diverged. Okay, so the nice thing about the direct comparison test is it's fairly simple to understand once you wrap your head around it. The hard part about the direct comparison test that we'll see in a minute is that it's not always easy to come up with something to use for comparison. So I've got a couple of examples here that are just kind of clarifying what's happening numerically when we talk about the direct comparison test. So here I've got 1 plus 1/2 plus 1/4 plus 1/8 and so on. Well, we know that one converges because we're essentially looking at 1 over 2 to the n power, so it's geometric. Well, if you look at that series, look at term by term. So we don't really know exactly what type of series we have on the right, but if you look term by term, you can see that each term in the series on the left is larger than the series on the right. Well, the larger of the two series converges. That means the smaller series is also going to have to converge. Okay, so that's sort of the idea there. And then in the reverse of that, here I've got essentially 1 over n if we started at n is equal to 2. And then this is just 2 over n. Well, notice that the smaller of the two series is diverging. That means the larger of the two series is also going to diverge. So that's the idea behind it. Now, when we are going to use this direct comparison test, essentially what we have to do is we have to figure out something to use for a comparison. And this is the hard part about it, is not only do we have to decide what to use, but the functions have to fall within the same order. And I'm saying functions because I'm talking about the rule that defines the terms in the series. Okay, so determine if the following series converge or diverge. So sometimes these are really easy to determine. So for example here, I'm going to use a direct comparison. And what I'm going to do is I want to think of something, when we're going to do a direct comparison, we want to think of something that's really, really easy to show convergence or divergence for. So for example here, notice how this sort of looks like a geometric series if the 2 wasn't there. So that's what I'm going to hope will work here. So 1 over 2 plus 3 to the n and 1 over 3 to the n. And now let's think about which one of those rules would result in larger values. So for the same corresponding n value. Since there's a 2 here, that's always going to make the denominator on the 1 over 2 plus 3 to the n a little bit bigger, which means the value will be a little bit smaller. So 1 over 3 to the n is always going to be bigger than 1 over 2 plus 3 to the n. So now let's look at this. If we were to look at this series from 1 to infinity of 1 over 3 to the n, that's the same as writing it like this, n equals 1 to infinity if we had 1/3 to the n. Well, that converges, right? And we know that converges because it's geometric. And our r value here is 1/3. Okay, so we have a reason that that one converges. Well, now look at the order that our 2 rules fell in here. The larger of the 2 converged, that means the smaller one also has to converge. So therefore, the sum of this series from 1 to infinity, 1 over 2 plus 3 to the n, also converges. And our reasoning for that would be direct comparison. So I'll say by direct comparison. Okay, so again, notice that I'm justifying how I know these things are converging. And this is the habit that I want you to get into, is not just saying something converges or diverges, actually explaining what your thought process is. All right, so let's look at another one. So there it seemed pretty simple, right? It was pretty obvious what to use for a comparison. Well, here's another rational function that we're going to try to use a direct comparison with. So we've got this series from 1 to infinity, 1 over 2 plus the square root of n. So the most obvious thing to do here would be maybe 1 over 2 plus square root of n. Let's compare that to 1 over square root of n, if this is, sort of treated like the last problem. Well, in this case, the 1 over 2 plus square root of n is a little smaller than 1 over square root of n. If that's true, what we're hoping is that the larger of the two would converge, right? But in this case, if I look at 1 over square root of n, well, that one diverges, and that one diverges by the p-series test. Well, what happened was the larger one diverged. That doesn't tell me anything about this other series. So this series from 1 to infinity of 1 over 2 plus square root of n, we still don't know anything about it. We don't know if it converges or diverges. So in this case, direct comparison is a little bit harder to use. So it doesn't mean I can't use direct comparison. It just means that it's harder to come up with something that I know will work. It's a rule that's going to behave in a similar way that I can, figure out the behavior of. So when we run into things like this, a lot of times we won't use the direct comparison test. We're going to use what's called the limit comparison test. So the limit comparison test is based on the idea of sort of looking at the behavior of the 2 series, and if the 2 series are behaving in the same way, then they're going to have the same resulting convergence or divergence. And the way we identify that is by using a limit. If we take the limit of the ratio of the rules for the terms, and if we get a number that's finite and positive, that means they behave the same way. If we get a number that's infinite, then we know that either, you know, they're not going to be, all right, so when we look at this test, essentially what we're doing is we're comparing two series, and we know that they're going to behave the same way based on a limit of the ratio of the rules for the two series. So for example, if I have two series that have an n squared, let's say we had like n squared plus n as one series rule, and we had n squared minus 2 as another series rule. Well, both of those have quadratic behavior, right? So I know that they're essentially going to behave the same way. If I took the ratio of those two rules, I would get a limit value of 1, which is finite and positive. When we take the limit of the ratio of the terms of the two series, if we get a number that's finite and positive, that means that they both behave the same way. They're either both converge or they both diverge. Okay, so let's take a look at an example here. So for example, let's say we were trying to do a direct comparison with this one. 1 over 2 to the n minus 1 and 1 over 2 to the n. So let's say we wanted to know, does 1 over 2 to the n minus 1 converge or diverge? Well, an easy comparison is 1 over 2 to the n. 1 over 2 to the n converges, right, because it's geometric. But the larger of the two series, that doesn't necessarily tell me anything about whether the 1 over 2 to the n minus 1 series is going to converge. But we can actually use these two as a comparison if we do a limit comparison. So what's been done down here is they got a ratio of the rules for the two series, which simplifies down into 2 to the n over 2 to the n minus 1. And now when you take the limit as n approaches infinity of the ratio of those two rules, you get 1. That means both of these series are going to behave the same way. So they're going to converge then, or the series we want to look at, the 1 over 2 to the n minus 1, is going to converge by the limit comparison test, because 1 over 2 to the n converges by the geometric series test. So it's a little bit of a multi-step process here, but it's actually really easy to use. And if you remember last time I told you that p-series test we were going to use all the time, this is where the p-series test becomes a very, very likely candidate for us to use when we're analyzing our series. All right, so I'm going to show you one of these just to give you a feel for how I want you to show your work on these, and then I'm going to have you try a couple of them. So we have this series that goes from 1 to infinity. It's 1 over 3n squared minus 2n minus 15. So what I want to think about is, what can I use as a comparison? So when it's a polynomial expression like this, I usually want to use that same polynomial in its most basic form. And what I mean by that is I have a 3n squared minus 2n minus 15. So what I'm thinking about is I want to use, instead of 1 over 3n squared, I want to use a 1 over n squared. And so the limit that we take here is just kind of a check. Do these series actually behave the same way? So I'm going to take the limit as n approaches infinity, and I'm going to do 1 over n squared. That's the rule I want to use, over 1 over 3n squared minus 2n minus 15. Okay, so are these comparable? Well, in the end, if I do my algebra here, I'm going to end up with 3n squared minus 2n minus 15 over n squared. And if I solve that limit out, I got a value of 3. That's finite and positive, so I know these two series are going to behave in the same way from a convergence standpoint. So that's my justification that I can use a limit comparison test. So now remember, I compared to 1 over n squared on purpose because I wanted something really easy to compare to. And I mean easy from the standpoint of it's easy for me to justify the convergence or the divergence of this series. So 1 over n squared, that converges by a p-series test, right? So I'm going to say that converges by a p-series test. And therefore, we can say that our series that we started with, the 1 over 3n squared minus 2n minus 15, we know that series converges by limit comparison. Okay, so it's a little bit of work to use a limit comparison when you have to write out your justification. But the nice thing is I can do a lot of these in my head now, because when I look at a series like that, I'm thinking immediately in my head, oh, I can compare that to a 1 over n squared. I know 1 over n squared converges, therefore this one's going to converge. So a lot of these where if I don't have to justify my work and I'm just doing a quick check, I can do a really quick check and I can tell you right off the bat whether it's going to converge or diverge. Okay, so there's 2 more of these here. And what I want you to do is pause the video and take a couple of minutes and work through these 2. You can probably tell just by looking at them how they're going to work out, but I want you to actually write out the steps, because this is what I'm going to require you to do when you have to work out these types of problems for me. All right, so here is the solution to the first one. And you can see I chose to compare it to 1 over square root of n, and I got a limit value of square root of 3. Now, it doesn't matter what order I write this expression in. I can flip this as long as I have the ratio of the 2 terms, right? The 2 rules for my terms. So let's say I had flipped it the other way. Rather than getting square root of 3 for my limit, I would have gotten 1 over square root of 3. Either way, both limits are finite and positive. So in the end, they're still going to show that they're going to behave the same way, regardless of the way I set up that ratio. Okay, so now 1 over square root of n I know diverges by the p-series test. Therefore, this series is also going to diverge. All right, and then the last one here. And again, I can just look at that. I'm essentially, when I look at that, I'm thinking 1 over n cubed. This is like a 1 over n cubed. I know that converges. This one's going to converge. But if I'm going to actually show that, you can see I've shown my limit here of the ratio of my terms. And this time, just to save a little bit of work, you can skip the steps if you want. And I'm showing that I have the ratio of n squared minus 10 over 4n to the 5th plus n squared, and I'm dividing that by 1 over n cubed. So I ended up with a limit of 1/4, which is finite and positive, so these behave the same way. I know that 1 over n cubed converges by the p-series test, therefore this one converges by limit comparison. So again, fairly easy to use. If you go back to that one that we were working earlier, and let me pull it back up here, the one that we looked at a little while ago, now that we know the limit comparison test, this would be a really good candidate for a limit comparison. And I can see just by looking at this, I know this one's going to diverge based on the fact that I know I'm going to compare to a 1 over square root of n in a situation like this. So again, direct comparison, every once in a great while we'll use it when it's convenient, but it's a lot more convenient for us typically to use a limit comparison test. All right, so the next test we're going to talk about here is called the ratio test. And the ratio test just works, if you remember back to when we were looking at how to show whether or not a series, we're looking at sequences, and we were talking about, does the sequence strictly increase or does it strictly decrease? Does it eventually increase, eventually decrease? So we looked at the ratio of terms. And that's what we're doing here, is we're looking at the ratio of the terms in our series. We're looking at 2 consecutive terms. We take the limit of that as the term number goes to infinity. If we get a number that's greater than 1, that means our series diverges, which kind of makes sense, because if we take a ratio of 2 consecutive terms, that would indicate that the terms are getting larger if I get a ratio greater than 1. If I get a ratio less than 1, that means the terms in the series are decreasing, and that would tell me it converges. If I get a ratio of exactly equal to 1, that tells me that this isn't a good test to use. I'm not getting any good information about this. So things that we were using with a limit comparison test, those would be good examples of things where a ratio test would not be a viable option. So when we're dealing with like polynomial rational expressions, those typically aren't good candidates for the ratio test. Those are better candidates for the limit comparison. All right, so I'm going to show you one of these, and then I'm going to have you try a couple of these as well. Now, the ratio test, the algebra on these can be a little bit tricky. So I want to make sure that we kind of talk through this a little bit. So we have this first one, -1 to the n over n cubed, or times n cubed over 3 to the n. Okay, so I gave you actually an alternating series here, which we haven't really talked about yet. One thing that your book doesn't go through with the ratio test is that the ratio test can be used for absolute convergence. And this is the way that I want you to actually use the ratio test, so we don't have to go back and redo the ratio test. So I put the ratio test here in the way that your book presents it, but the reality is this test also applies if we take the absolute value of the ratio of the terms. So that's really the way that we're going to use the ratio test when we go through this. And you'll see when we get to looking at our Taylor series and we're finding what we call an interval of convergence later, that use of the absolute value is something that's going to be really important to us. Okay, so what I'm going to do here is I'm going to take the ratio of terms. So I'm going to take the limit as n goes to infinity, and I'm going to do the n plus 1 term over the n term. So I've got negative 1 to the n plus 1 times n plus 1 cubed over 3n plus 1. So that's the n plus 1 term. Anywhere there was an n, I plugged in an n plus 1. And now this is the nth term. It's just the term that or the expression I was given, negative 1 to the n cubed over 3 to the n. And now remember, we're going to do the absolute value of this. When I do that, that essentially tells me these things that make it alternate, I don't have to worry about those anymore. So now let's rewrite this in a simplified form. We've got the limit as n goes to infinity. And what I've got here is, let's see, n plus 1 cubed over 3 to, or times 3 to the n over 3 to the n plus 1 times n cubed. Okay, so now let's think about this. So I've still got my absolute value here. We can leave it there. It doesn't really matter at this point because we already dealt with it, but I'm going to leave it there just because that's the habit that I want you to get into. Okay, so at this point, let's kind of group the things that are the same together. So what I mean by that is I've got these geometric expressions, or I guess exponential expressions, 3 to the n and 3 to the n plus 1. If I divide that out, I've essentially just got a 3 in the denominator. So that's going to be 1/3. And then if I look at these cubic expressions, I essentially have n plus 1 over n all cubed. And we're taking the limit of that as n approaches infinity. Well, that expression of the n plus 1 over n cubed, as n gets infinitely large, the 1 doesn't really matter, right? The plus 1 doesn't really matter anymore. So I end up with just a value for this limit of 1/3, which is less than 1. So that tells me that this series converges, and that would be by the ratio test. Okay, so it's not horribly difficult to do, but it can be a little bit tricky, especially when you start involving factorials into the situation, and you just have to be really, really careful with your algebra as you go through the steps here, because it's very, very easy to make a mistake. Okay, so I've got 3 more of these here that I want you to try. The next one, we have n to the n over n factorial. You may be able to tell just by looking at that that's going to diverge. I still want you to do it with the ratio test, and then go ahead and finish these last 2 as well. So there's 3 of them there. I want you to try it. So just pause the video. Do your best with them. When you unpause it, I'll show you the solution. Okay, so here's that next one, the n to the n over n factorial. You can see with my ratio test kind of what happened here. Now, I just want to explain this algebra really quickly. So I still did the same idea. I did the n plus 1 term divided by the n term. Notice here I had this n plus 1 factorial, and I had over here an n factorial. So I really kind of need that factorial to cancel out. So what I did is I factored the n plus 1 term out of the factorial. Because remember that really, if I were to think about n plus 1 factorial, it would be n plus 1 n plus 1 times n minus 1 times n minus 2 times n minus 3 times n minus 4 and so on, all the way down till I got to 1. So in the end here, I can factor a term out of it, and that allows me to cancel out the factorial. And then I also grouped together the fact that I had the n plus 1 over n, they were both to the n power. Now notice this limit. If you don't recognize that limit, you might have to use L'Hopital's rule there, but a lot of people will recognize that that is actually the definition of E. If you think of that as 1 plus 1 over n to the n power, that actually is equal to E. E is greater than 1. That means this series is going to diverge. Okay, so let's take a look at the next one here. So the next one, a little bit easier actually. We've got n squared 2 to the n plus 1 over 3 to the n. And you can see that I first started with my n plus 1 term divided by my n term. So I usually go straight to the multiplication step just to save a little bit of writing, because it's still technically the same thing as showing that I'm dividing the terms. And then from there I simplified, I grouped everything together that I could. And you can see we get 2/3 for our limit this time, which is less than 1. And that means that my series is going to converge. All right, and then the last one here was another alternating series. So this is an example of one where it doesn't work. Remember I told you with the polynomial expressions, a lot of times it's not going to work with a ratio test. This one would have been a much better candidate for a limit comparison. And in fact, this would have been even better with an alternating series test, but we haven't talked about that yet. So really what we'd want to use here is not available to us. But if I do this with a ratio test, I can take the alternating part out of it. The problem that I run into here is that I got a limit value of 1. A limit value of 1 means my ratio test isn't giving me any information, so I've got to use a different test. And like I said, in the end, my best option there would be an alternating series test. Okay, so last type of test that we're going to look at here is called the root test. This one is kind of similar to the ratio test, but it's used in a particular type of situation. And it's a situation when we have something we're taking like an nth root, or in this case, they're using the index k. But if we take like the nth root or the k root of something, then we can essentially figure out what the behavior is going to be by taking the limit of that expression. So where this is going to be used a lot is when we have things that are raised to the n power or raised to the k power. So notice the conclusions here. These are essentially the same as what I had for my ratio test. If I go through and I take that nth root or that kth root, and I take that limit and I get a number that is greater than 1, that means it diverges. If I get a number less than 1, that means it converges. And if I get a number equal to 1, that means that this isn't a good test to use. Now, remember, essentially what we're doing here is we're kind of trying to just look at what's inside the radical. So we're trying to look at the radicand and decide convergence based on the behavior of the radicand. Okay, so here's an example. I'm going to show you one of these. These are actually pretty easy to do. I've got 1 over n to the n power. So I'm recognizing right away this looks like in a root test that I could use here. So I'm going to take the limit as n goes to infinity, and I'm going to take the nth root of 1 over n to the n. And when I do that, that's the same as the limit as n goes to infinity of 1 over n. Now evaluate that limit. We got 0, which is less than 1. That means this one converges. Okay, and that converges by the root test, right? So that would be root test. Okay, and similarly, you can look at the next one. I'm not going to show all the steps here, but you can kind of think through this one. And this eventually, I want you to get to the point where a lot of these, you can just look at them and tell whether they're going to converge or diverge. So for this one, you can think, okay, everything's raised to the n power. This obviously looks like a root test. If I take the nth root, I would have 2n plus 3 over 3n plus 2. Take the limit of that, it's going to give me 2/3. So I know this one is also going to converge. Okay, now if you're actually going to use the root test, yes, you need to show all the steps and you need to justify it. But if you're just doing a quick check and you want to see convergence, that's kind of how I would do that in my head to justify whether it converges or not. Okay, so when you go through this assignment, keep in mind within some of these tests, some of the previous tests are going to show up, right? Especially that p-series test. So it doesn't mean that just because we're doing limit comparison and direct comparison and everything else that all the rest of them go away. You know, there's geometric series tests showed up in here. So within these tests, you're going to see other tests often appearing. So don't forget about those. They're just now embedded within these new tests that we're going to use.